All right, so homework 7 I've just handed out. It's due next Thursday, but we're not going to meet as a class next Thursday because I'm going down to Clemson to work on the FE exam. So what you'll need to do is submit the homework by 12 o'clock. So write in the blank there, 12 p.m. And by my door is a black metal box hanging on the wall. It's wire mesh. Put it in there, and the grader's going to pick it up by 12 so that if you turn it in at 12:05, he's going to rip it up, throw it in the garbage. But if you turn it in at 11:59, he'll grade it, he'll be happy. It's due at 12 o'clock next Thursday. All right, any questions about that or comments? No more than it has been for the rest of the semester. All right, other questions? Okay, so the assignment will be due next Thursday. Since I'll be gone, the class recording will be posted online, so the lecture that we'd normally have together will just be recorded only. You know, these recorded lectures that I do, like I'm doing right now, you can't see what I'm writing on the board, but when I miss class because I'm going on a meeting or for a conference, then I will use the pencast to edit in any written examples, and so it will be a full normal lecture. All right, we're going to start talking about what I think is finally the payoff for the class. You've been learning all this theory, and my guess is that most of the people in this class, because they're engineers, enjoy problem solving more than theory. If you were more theoretically oriented, maybe you'd be a mathematician or a scientist, but you're an engineer, which means you're more application oriented. You want to do things with what you've learned. Finally, we're going to get to start to do some useful things, and you're going to be learning skills that you can actually apply in an engineering application. You could go to an engineering design firm and solve problems that they actually have, things that they need you to know. It's unlikely that you'll ever go to a design firm and they'll ask you to put together an evaporation spreadsheet. And that's not, you need to know how evaporation works and the fundamentals of it in order to use the tools I'm about to teach you, but this is finally the heart and what we've been working up to. So the NRCS rainfall runoff model is a way of answering the big questions in the course. So I've blanked out this slide. What do you think are the big questions of the course? We've talked about the relationship between hydraulics and hydrology. So really, what are we trying to address in all the theoretical study we've done so far? What is the, I'm going to add runoff, flow rate coming out of an area. Very good. Any thoughts or additions to that? Okay. Yeah, what is the flow rate and sort of what does the hydrograph look like? Because it's not just the flow rate, but it's maybe how long a certain flow rate is lasting, what volume is coming out, because what are the things that the engineer is going to design? The engineer is going to design channels, pipes, ponds, maybe levees. So you have to know what's the water elevation, how much of it is there, how long is it going to last. You just want to characterize all of the temporal and spatial characteristics of a storm. You know, that water that's falling out of the sky, when is it arriving at a certain point, and how much of it will there be? So for an area of interest, what are the runoff characteristics? How much? When? So what we've looked at so far is we've studied rainfall, and you've learned about return period. Return period is when we say a 2-year storm, a 5-year storm. That's not duration. That's how frequently it comes back on average. It's like a probability. In any given year, there's a 10% chance of experiencing a 10-year storm. In any given year, there's a 4% chance of experiencing a 25-year storm, and so on. So return period is those big events and how often they come around and how much water is there. Do you remember what's the data source for accessing return period and amount data? There's a website. Do you remember the name of that website? Okay, what you're remembering, the PRISM at the Oregon University, that was a good spatial distribution website. That's something that tells you how much rain is there over a map area. There was a different one for return period. It's the one where you could click on a spot and it generates the IDF curve right for you. It was NOAA. Yeah. It's the Precipitation Data Frequency Server. So that's where you can go and get an IDF curve for some project area that you're interested in. And temporal distribution. We looked at some typical storm shapes. Does anybody remember what we taught, like the name of those storm shapes? Those shapes look like this. One of them is really steep. Another one is a little more gradual. Anybody remember the names that are associated with the temporal distribution of storm events? Type 1, Type 2, yeah, exactly, 2A. And so that's called the SCS storm distributions. And so return period, temporal distribution is this. Spatial distribution is looking at a map and finding out in Miami how much rain is there compared to in Boise. Okay, so we studied rainfall extensively. We've talked about infiltration. We've used some rough, kind of like not very intellectually stimulating, the Horton infiltration model, which is just plugging in some empirical equations. And we also did the green-amped method for infiltration, which is a little more exciting because we get to use goal-seek and it's an implicit equation. So green-amped method, the Horton infiltration method, and both of those we're looking at how much water gets into the ground and at what rate. We're going to extend our analysis of infiltration by looking at specific types of soil and what's on top of the soil. The assignment I've given you today, you're going to go to a Department of Agriculture website, and you'd think, the Department of Agriculture, that's strange. You know, like, why would the organization that inspects steaks have anything to do with hydrology? Because the USDA, they're the ones who inspect meat, you know? Like when you buy Bar S Franks at Walmart that says USDA inspected. Well, what they also do is they study the soil, because how productive crops are depends greatly on different soil types. And so you're going to go to a special USDA database, and you could do it today after class. There's no reason not to start poking around. And you can draw a little map, and it will tell you what the soil looks like in the area of interest. So clay soils infiltrate poorly, as you know, because the hydraulic conductivity is low. Sandy soils infiltrate well. We're going to give grades, like letter grades, to soil types, A, B, C, and D. And those letter grades we give to soil types along with what's on top of it, the land use, whether it's concrete on top of the soil or forest on top of the soil. That combination of soil and land use will allow us to come up with something that makes it very easy to calculate infiltration, or at least to estimate it. These are all just estimates in hydrology. The real processes are far too complicated for us to know on a molecular level where each molecule is going in the watershed. So we just have come up with empirical estimates that do an okay job of guessing at what might happen. Antecedent means before the event. And I've mentioned a couple of times that I've been studying a couple of watersheds in the area, and it's just really been breaking my heart that I didn't get my stream gauges into the field a couple weeks earlier than I did, because you may remember that in September we had a really long dry period. There was like 3 weeks with no rain in September, and so the ground was all dried out, and then it started raining pretty hard. Unfortunately, I didn't get my stream gauges out in the field until after it started raining. It would have been really interesting to look at how does the totally dried out watershed compare when there's a storm for the first time in 3 weeks. What does that runoff compare to? It's already been raining 3 days in the past. Every day for the last 3 days it's been raining, and then it's going to rain today. Even though the watershed has the same soil type, the same land use, the fact that the storms were dry versus the storms were wet in the immediate future changes the infiltration rate. And so antecedent moisture is something that we're going to keep track of as we study the rate of infiltration for watersheds. You already remember the abstractions like interception, evaporation, surface wetting. These are just all of the things that get in the way of the runoff. And there was a phrase that said the abstractions had to be accomplished before there would be surface flow. And so it's like paying a toll or paying a tax, that there's only going to be runoff if there's more rainfall than there is infiltration and abstractions. The rainfall has to exceed both of these or else there won't be any runoff. And sometimes that's true when it's just a fine mist. The rain is just enough to maybe get your glasses spotted and wet, but not wet enough to start causing puddles. It's because the abstractions weren't satisfied or the infiltration rate exceeded the rainfall. So finally, you can have runoff if those things are exceeded. And what we're going to do in modeling, models can be equations, they can be small-scale devices that represent a large-scale thing. The models that ultimately you're going to create, not in this homework but in the next one, are software models that simulate a storm, a hypothetical storm, and how a watershed is going to behave in that storm. And so it will tell you what the hydrograph shape looks like. Some of the kind of crude models, like the rational method, that's a model. Q equals CIA, the rational method, it tells you what is the peak flow. It assumes a triangular hydrograph. It doesn't necessarily nail down the time to peak very well. It overestimates generally. C is hard to estimate. It's more of an art than a science. So the rational method is a crude model, but we're going to look at some sophisticated models that we can actually feel good about and confident that we're getting within maybe 20 or 30% of the true answer. And that sounds pretty crude, right? That we're going to go to all this work and then our runoff peak flow rate is only about within 20 or 30% of the true value, but it's good enough. Hydrology is an art as much as a science in some ways. We haven't talked about routing yet, not very much. We did a little bit. We talked about, remember that really good drawing I did of a stream and a bucket? If you pour here's our stream, and you've got a bucket of water, and when you pour that water, let's say that this bucket is 5 gallons. If I pour it here, then by the time it reaches a very close spot, that 5 gallons will come past like this. There's a big wave of water and then it's finished. And that wave is moving down, but the further away I get, by the time the water gets to here, maybe the water has spread out a little bit because there's friction and resistance. That big, tall glob of water that I pour in is getting spread out and it's draining slowly because of the frictional contact with the surface. And so that effect is something that we call routing. Routing just looks at transit time of water in the watershed and in the stream. How long does it take for water to get between 2 points? Time of concentration is an example of a routing question. Time of concentration is how long for the water at the furthest point of the watershed to travel over the surface and then in the channel and finally arriving at the outlet. So that's a routing question. Also, concentrated flow. Concentrated means that the water is together. It's not spread out over a sheet like it is on surface flow, but when it gets into a channel, what kind of delay is there as water flows from upstream to downstream? Because it takes a little bit of time and that can have an effect on the implications. So the last thing that we're going to look at in the semester, we won't have as much time to look at as I'd like, but hydraulic sizing which is actually kind of where we started when we were figuring out how big should a culvert be. So we've already done a little bit of hydraulic sizing. We did partial flumes, which is related to hydraulic sizing. Floodplain management is similar to what you may remember from engineering economy. When you have different alternatives, you can do one project or another project, and how much money will you earn from each project? With hydrology, there are a lot of tie-ins to economics because when a dam is built, for example, a flood control dam, they have to look at how much damage is that dam going to avoid. Last semester in fluid mechanics, I showed you an overhead picture of a dam called Oahe Dam, which is in North Dakota on the Missouri River. And that dam is estimated to generate $150 million a year in benefits, meaning it would flood more often than it does if it wasn't for that dam. And so we'll take a look at some of the decisions that a floodplain manager would make about, does it make economic sense to lift the foundation of buildings, existing buildings, or is it economically feasible to widen a channel and dredge it to avoid flooding? So just how does knowing how often it's going to rain, we're going all the way from rainfall to how you should spend your money. Because there's a tie between how much it's going to rain and what the flooding is going to do and what kind of projects a city should engage in. The flood wall in Huntington is an example of that. A decision was made. We don't know how much of that decision was based in engineering analysis and how much of it was based in public hysteria. Like people were just freaked out by the flood that had happened a few years ago, and so they threw up a concrete flood wall. But we'll go through some of the methods that are similar to benefit to cost analysis that you may remember from engineering economy. So these are the big questions of the course. It's kind of an overview of where we've been and where we're going. So right now, we're on this bullet point, runoff modeling. I think it's the funnest part of the course. You could use a little fun, right? All right. So we're going from rainfall to runoff, the model. And what the NRCS method does is it takes the rainfall hydrograph and comes up with a hydrograph. So what you put in is how rainy it is. That's not the only thing you have to put in. You also have to tell it what the soil is like, what is the land cover, how steep is the slope of the ground, the stream characteristics like the density of the stream, how wide is the channel, how steep is the channel, the geometry. So that's actually kind of a lot of things that we have to tell it about the watershed before we can get our runoff hydrograph. You know, it's a law that the fewer variables a model has, the more crude approximation the output is going to be. And so last semester in hydraulic engineering, you remember that in pipe flow, sometimes we would use the Hayes-Williams equation, and sometimes we would use the Darcy-Weisbach equation. Hayes-Williams is the one where there's just some constant friction factor C sub h. And it didn't matter what the flow rate was, it didn't matter what the pipe diameter was, it's just based on what the pipe is made out of, there's some roughness coefficient that's unchanging. And so that was easy to use, but it was pretty crude because what we knew when we used the Darcy-Weisbach equation is calculating the F friction factor was a function of the diameter of the pipe, the Reynolds number, the temperature of the water. There's so many different variables that went into calculating the more sophisticated roughness value F. And so watershed modeling has the same principle that here's an easy model that doesn't ask very much from us, but it's not very accurate. And the NRCS method is an upgrade from the rational method because it's asking you to give it more information, but the results are a lot more reliable. And so the method that we'll step through is looking at the soil and land characteristics, try and estimate what's happening with abstractions, retention, and initial runoff, and then using a unit hydrograph shape. And you've already seen what unit hydrographs are like. The NRCS method has their own typical unit hydrograph that they translate a peak flow rate into the temporal distribution of the flow using their unit hydrograph. So here's starting to look at some equations. And let's look at the figure before we go through some of the definitions here. This figure is declining potential rate of infiltration. So we've got both a hydrograph, and that's what these different steps are. The steps are it rained a certain amount, and then it rained a little more, and then it rained a lot, and then the rainfall decreased. It looks like there's 1, 2, 3, 4, 5 different time steps here. Maybe it's hourly, maybe it's every 30 minutes, but we've got how much it was raining. This is a rate. And at the same time, the soil infiltration rate was decreasing because all of the voids were starting to fill up. The soil suction head was decreasing. What the NRCS method says is, let's break these two things, the infiltration and the hydrograph, let's break it up into parts. And we'll say that some of the rainfall that doesn't run off is the initial abstraction. Some of the rainfall is water that's retained, and retained water includes water that is infiltrated. And then anything above the line is precipitation excess. And so the NRCS method is trying to find out how much of the precipitation turns into precipitation excess. So here is the relationship. We don't actually use this one in problem solving, but this is the conceptual model that the equations are actually derived from. It's saying that there's a ratio of the retained water to storage. S means storage. It's the maximum amount of water that a watershed can retain. The ratio of the retention in the watershed to its overall maximum storage is similar to that of the precipitation excess to the initial precipitation amount minus the initial abstraction. So we rearrange this expression eventually, and we just estimate that the initial abstraction is about 20% of the maximum storage of the watershed. This is a simplification that's often used in place of a lot of detailed data about, if you don't know how thick the vegetative cover is, and you don't know how much surface wetting there has to be, then you can just empirically estimate how much initial abstraction there might be based on the land use and the soil type. So we wouldn't have to make this assumption if we could say how much interception, how much surface wetting, and just small unconnected ponds there are. But we often don't have that level of detail, so we substitute this instead. So we have to do mass balance. And mass balance is just saying what comes in and what goes out determines the amount of storage inside of a control volume. And the watershed is the control volume in the NRCS method. It's saying, let's look at the water that's coming in, and in a short duration rainfall event, we exclude the other concerns like that groundwater might be migrating side to side in and out of the watershed. We're just looking at what's happening at the surface. And what's happening at the surface is that rainfall falls onto the watershed. So it comes in, and what goes out is runoff. And any difference has to be accounted for by accumulation, and so initial abstraction and retention is the accumulation term. So here is a way that we calculate that storage, and CN stands for curve number. Curve numbers are calculated based on the soil class. It's a grade of A through D, and the land use. There's tables where we can look up for certain soil types and certain land use what is the corresponding curve number. It's a lot more sophisticated and accurate than those tables that we had for C value. Same kind of idea, but it's more scientific and less approximate to identify the curve number. So you can calculate the storage based on the curve number, and then once we know the storage, for a certain storm depth, P is the depth of the storm, then we can calculate how much of it will be excess, precipitation excess. If the precipitation is greater than 20% of the storage, then you'll get runoff. If the precipitation is less than 20% of the storage, you just assume that there's no runoff. The precipitation excess is 0. Okay, so here's an illustration of how to use these equations. What's the rainfall excess depth for a watershed that has a curve number of 70? We've got 0.7 inches of rainfall or 3.5 inches of rainfall. 0.7 inches of rainfall is a storm. If it was a 24-hour duration, that would be a storm you'd see a couple of times a year in these parts. Now 3.5 inches of rain, that's maybe now getting into the range of like a 2 to 5 year storm. You wouldn't see that much rain in a 24-hour period on an annual basis. So let's start with part A. For P equals 0.7 inches and curve number of 70, you should first of all calculate the initial abstraction, then make the determination is P greater than initial abstraction. And if yes, well, if P is P less than. So if P is less than, if yes, no runoff. All right, so why don't you substitute those numbers in there for the curve number of 70, find out what is storage, and we're assuming that the initial abstraction is 0.2 times S. Okay, in this first case, there's no rainfall excess. There won't be any rainfall excess, meaning there won't be any runoff, because this 0.7 inches of rain doesn't satisfy all of the abstractions. So the abstractions have to be satisfied before there's enough water left over to start running off. What about part B, where there's a different storm that has 3.5 inches of rain? Okay, so in this other storm of 3.5 inches of rain, P equals 3.5 inches. We've already checked the initial abstraction, so we know that P is greater than I sub A, so there will be rainfall excess. So we already have S. We previously calculated that S is 4.286 inches for this watershed. So let's calculate the precipitation excess. P minus 0.2 of S, that numerator term is squared. P plus 0.8 S, so we've got 3.5 inches minus 0.2 of 4.286 inches. And we square this numerator term, and then 3.5 inches plus 0.8 times storage of 4.286 inches. Okay, 6.984 in the numerator, 6.929 the denominator. The precipitation excess is going to be 1.008 inches. So of the 3.5 inches of rainfall, only 1 inch is going to go into rainfall excess. Where's the rest of the water? Well, we previously knew that the initial abstraction we calculated in the first part of the problem, initial abstraction is 0.857 inches. So where's the rest of the water? It's in retention, F sub A. So the retention, 1.635 inches. So this is retention. This is initial abstraction. And then this is precipitation excess. There's some synonyms that you need to be acquainted with. Sometimes precipitation excess is called rainfall excess. Sometimes we just go ahead and call it runoff, even though it's a depth. So we might call P sub E, might also call it rainfall excess, or we might just call it runoff. We're really being sloppy when we call it runoff, though, because usually runoff is reserved for when we've converted it into a volume or a volumetric flow rate. And at this point, it's just a depth. It's meaning that, 3.5 inches, which is about this much water, fell over the surface, and 1 inch is what is going to go over towards the outlet. So if you know the area, then you could multiply the area of the watershed by this precipitation excess, and that'll tell you the total volume that's going to make its way towards the outlet. The rest of this water is what gets stuck and accumulated inside the watershed. And it's going to migrate eventually somewhere. It'll eventually evaporate, or it'll eventually infiltrate out of the watershed. But that's in the much longer term than this short-term movement that's associated with precipitation excess. All right. Any questions about this one? Yeah.
So did you find FA using that equation or just subtracting it?
Just subtracting it. Yeah, because there's only a few places the water can be. So here's the precipitation is everything. And so this diagram is showing that the precipitation is broken up into IA, precipitation excess, and the only other component is F sub A.
What if we use that top equation? Should we use the same answer?
You did it that way? Yeah. Glad to have that confirmed. Caution, this is traditional units only. The curve numbers that are provided are already formatted so that when you put the curve numbers into the storage equation, you're going to get a depth in inches. So that's one thing that you need to be aware of, is that if we look at a table of curve numbers, then it'll be inches as depth. So here I'm giving you a hint on homework 9, and you can do this in time steps. And what this is saying is that if you want to know how much water is in a certain place at a certain time, then use the precipitation amount till that time. Now, not all of these terms are at a certain time. Storage is a constant. Initial abstraction is a constant. But you can find out how much water is retained up to time t by putting in the precipitation up to that time t. So just maybe put a little note in the margin that come back to this hint when you're working on the homework assignment. So how do you know what curve number to calculate? Like in the problem statement here where it just said curve number is equal to 70, that's not how it works in the real world. If you're an intern for an engineering firm and they say, I need you to calculate the curve number for a watershed, what you do is you'd start by understanding the soil in the area. And that's why on the homework assignment I'm asking you to go to the U.S. Department of Agriculture website, is because they're the ones in the U.S. who classify soils. And the hydrologic soil group that the grade that they assign is based on the infiltration rate when they do an infiltration test. You remember the double ring penetrometer that we looked at and the single ring? They'll look at how quickly water infiltrates into the soil on a minimum basis. How many inches per hour of water gets in there. And a group A soil is characteristic of usually deep sands or a loess soil, aggregated silts, but that's what usually are classified group A. But how do you know whether it's a group A is from this penetration test. Gravelly soils are going to go in there as well. And so you can see that group C soils are pretty low infiltration, and group D are those that are just, they accept no water on a minimum basis. When they're wet, they become a barrier to any additional moisture traveling through them. So I have on my property actually quite a lot of soils that are considered plastic clays. It's like almost a toy. The soil there is just so squishy and useless, and water just puddles right on top of it, and it takes them a super long time to dry out. Most of the watersheds in this part of the state are C and D. We'll get into classifying soils, and you'll see that there's very few B-rated soils in the area. And an A soil, I don't think I've ever seen an A soil, except for unless maybe it was brought in, like soil that was trucked in and put under somebody's yard just so that they could grow grass. But besides that, we have C and D soils. Here's some tables that show you if you've got a certain hydrologic soil group. So look, there's different columns. Each of these columns is associated with a different soil type. So lawn, if it's a golf course, a cemetery, or a park where there's a lot of open grass, they are classifying the curve number based on the condition of the grass. Like poor condition grass is the side of the road where people are walking on it and tramping down the soil, and it's patchy, it hasn't grown very well. A good condition grass is going to be like a nice golf course where they put a lot of effort in maintaining the consistency of that grass. So what is the trend is that the curve number goes up as the soil group goes from A to D. So what does that mean? It means that there's going to be less storage for a D soil than there is for an A soil. So look at the formula here. If the curve number is in the denominator, like it is for the storage term, if you have a big curve number, so like a clay soil underneath, then your storage is going to be low. But if you have a small curve number, if you've got a small curve number, then this first term is going to be big, and then you subtract 10 out of that. There will be a lot of storage capacity. So we've got lots of different land uses, everything from lawns to gravel roads, dirt roads, paved roads. residential lots based on their size. So why do you suppose that a residential lot that's a 1/4 acre around here, if it was on group C soils, it would have a curve number of 83, versus if it's on a large lot, a 2-acre lot, the curve number would be 77. Like, why the justification for that difference? 83 is going to give you lots of runoff, 73 will give you less. Why is it that the lot size of the residential area has an impact?
Because you could put your house on a smaller area.
Okay, so you're thinking about what's on the lot. You've got, here's the lot, part of it's going to be a house, and what's up with the house? Well, that roof is impervious area. So it's, everything that falls onto the roof is going to run off. There's no infiltration on through the house. There's also, you know, like the driveway, and maybe they put in a concrete walk, and they have a back porch. And so if you've got a small lot, a greater fraction of it is impervious area, whereas if you've got a large 2-acre lot, then that's those people who just must like to do nothing but mow and mow and mow all Saturday long, because you see some of the people around here that have these enormous yards, and most of it's grass, which is good because it helps out reducing peak runoff for a watershed. You know, if they carved that up into tiny little lots, then more of it would be house area, and that's bad because there's too much peak runoff. So that's one of the trends. The trend that lot size plays a role, soil type plays a role, and if you, streets and roads, 98, 98, 98, 98, it doesn't matter what the soil type is, because the road cover itself is an impervious surface. So it doesn't matter if there's a nice, well-drained gravel underneath your concrete, the concrete still isn't going to allow infiltration, whether it's well-drained gravel or plastic clays underneath. Here's some other more rural curve numbers. You can see that the type of grass plays a role, the type of trees that are planted, whether it's deciduous or evergreen and so on. In addition to, I said the USDA has soil maps, there's also a really nice GIS database that's called the National Land Cover Database, NLC, National Land, yeah, NCLD, National Land Cover Database, NLCD. And they just released the 2011 survey. So it's they flew over the entire United States in airplanes, and they took a picture of the ground, and then they classified it. Is that asphalt? Is it farmland? Is it grassy? Is it a lake? And they've done that in, I think the resolution of it is, it's either 90 or 100 meters. So every pixel, like, they've broken up the entire United States into 100 by 100 grids, and they'll tell you what it is. And so if you've got a large watershed, you can get one layer of GIS data that's the land use, one layer of GIS data that's the soil type, and then you can have really fine resolution of the curve number piece by piece by piece for your whole watershed. And it's a very effective way of knowing what's out there. Antecedent moisture condition is what we talked about, where if it's been very dry in several days before a storm, the watershed will have a different response to if it's been very wet in several days before the storm. What this says is that if you normally have a type 2 kind of a soil, then how do you know what antecedent moisture group are you in? Type 2 is kind of the baseline. During the summertime, during the growing season, it assumes that in the 5 days before that you've got 1.4 to 2.1 inches of rain. And so the curve numbers that we've been looking at here, these are all based on antecedent moisture group 2. But if it's been very dry, so if it's been dry, then you would need to convert the curve number to adjust for how dry it's been. And this is the formula. The top formula is how you would convert if it's been very dry. And this bottom one, where it's saying CN3, that's how you would find a modified curve number if it's been very wet. And so this one will make your curve number smaller, the one on top, because if it's been dry, it'll make your curve number smaller. And this one will make the curve number bigger. Take a look at notes. I'm wondering what we're not going to be able to get to today. We'll do this example, and then I think we'll be out of time. So curve number estimation. Let's say we've got residential quarter-acre lot on Class B soil. Let's go back to the table and make sure that what it says here. It says that that should be a curve number of 75. Let's just double check that that's true. I don't know if you've got microscopic vision and can see. Good. It's a quarter-acre residential lot, Class B soil. So quarter-acre residential, Class B soil, 75. Okay, good. That's where that came from. We've got ordinarily curve number Class 2 conditions is 75. So what would be the curve number if there had been no rain in the last 5 days? So we are in the, it doesn't matter whether we're in the dormant season or the growing season. No rain would put us into Class 1. So we need to find out what is the curve number under dry conditions. Then the empirical formula for that is 4.2 times the curve number of 75 divided by 10 minus 0.058 times 75. And it's remarkable to see that it would bring the curve number all the way down to 56. You haven't done a lot of modeling yet, so you don't have a basis to know whether that's a little or a lot, but if you've got this curve number, it's going to have to rain and rain and rain before you see any runoff. It's going to be completely different performance than a curve number of 75. 56 is super low. And so dry conditions can really, really radically change how a watershed behaves. So the second case says, what if during July, meaning during the growing season, it had rained 3 inches in the past 3 days? So that puts us into group 3. So what is the group 3 converted curve number? So it's been wet, in other words. So if it's been wet, then we can say 23 times 75, 10 plus 0.13 times 75, and this is going to bring the curve number up to 87, which is also just like a monumental shift. I mean, that's the effect of it having been wet in the days before is going to be as big as if it was like half of the watershed was paved with asphalt. It's going to have a similar effect on the amount of runoff. It's going to be a gusher. If we get a lot of rain during this next storm, when it's been so wet in the previous days, it's really going to have a radical impact. So it's really easy to let the automated system do all these calculations, but the automated system is not going to make this conversion. So when you're setting up watershed models, you always in the back of your mind need to think, what's the antecedent moisture condition? Because it can just totally wreck a model if you've set it up without considering when the event is and how much rain there's been prior to that. Okay, that's it for today. I'd encourage you to get an early start on the homework, and if you've got questions on it, feel free to stop by to see me, and we will get together again on Tuesday.